The other thing we're going to look at today is instantaneous velocity. If s of t is the position function of an object moving along a line, then the change in s over the change in t represents the average velocity of the object over a time interval of length delta t. So the velocity function ds dt represents the instantaneous velocity of the object, the rate of change of position with respect to time. In other words, the velocity can be found by taking the derivative of the position function. The instantaneous rate of change of velocity with respect to time we call acceleration. So acceleration is the derivative of the velocity function, or the second derivative of the position function. So we're going to look at one example here. A particle moves along a straight line. For t greater than or equal to 0, the position of the particle is given by s of t equals t cubed minus 6t squared plus 9t, where t is measured in seconds and s is in meters. We want to do 4 things here. We want to find the velocity at any time t. We want to find the acceleration of the particle at any time t. We want to know when is the particle at rest, and we want to describe the motion of the particle. In particular, we want to know at what values of t does the particle change directions. So the first and the second parts here are really easy. We know our position function, because that's what's given to us here. S of t equals t cubed minus 6t squared plus 9t. So to find the velocity at any point in t, we just need to find the derivative of the position function. So here we can say that our velocity at any point t is going to be 3t squared minus 12t plus 9. Then, if we want to find the acceleration of the particle at any point in time, acceleration is just the derivative of our velocity function, or the second derivative of our position function. So here our acceleration at any point in time t is going to be the derivative of this velocity function we just found. So it's going to be 6t minus 12. So then we want to know when is the particle at rest, which is a little bit trickier because then we need to think about it. Well, we know that the particle is going to be at rest when its velocity is 0. So if we take our velocity function and set it equal to 0, then we could have 0 equals 3t squared minus 12t plus 9. And that gives us an equation to solve for t. This is just a quadratic. We've solved equations like this like 20 million times last year. If we look at all of these terms over on the right here, their greatest common factor is 3, so you could factor a 3 out of all of them. So we could say 0 equals 3 times t squared minus 4t plus 3. So then if we look at our quadratic here, we want to see if that's factorable, or we could use a quadratic formula if you prefer to jump right into that. To try and factor this, we'll look at our first term here. What multiplies together to give us t squared? Well, that would just be t and t. We look at our last term here. What multiplies together to give us 3? Well, only 1 and 3 multiply together to give us 3. To multiply to a positive and add up to a negative To get our b value here, they both need to be negatives. So then if we take this and FOIL it back together, t times t is t squared, t times negative 3 is negative 3t, negative 1 times t is negative 1t, that negative 3 and negative 1t add up to negative 4t, and negative 1 times negative 3 is positive 3. So this is the correct factorization. So then if we take each of our factors that have a t involved and set them equal to 0, we can solve for t. So we have t minus 1 equals 0, t minus 3 equals 0, which means that t is 1 and t is 3. So the particle is at rest at 1 second and at 3 seconds. And then the last question asks us to describe the motion of the particle. Now, anytime you see the words describe, that means that you probably want to do this in sentences. A couple of words is not going to be enough to describe something. So we want to say what is going on with the particle and be as specific as we possibly can. So in order to describe what's going on with the particle, it's going to help us to look at the graph of the particle's velocity. So let me add in another page here. So if we graph the particle's velocity, we see that we get a quadratic. Nice parabola. So we already found in the previous section that at 1 second and at 3 seconds, the particle is at rest. And we know we're only looking at times greater than or equal to 0 seconds. So we are not looking at negative times. Negative times are not a thing. So we want to know what's going on the rest of the time here when our particle is not at rest, when we're not on the x-axis there. Well, we really just need to look at what are the signs on the rest of the values. What are the signs on the y values? Are they positives or are they negatives? If we have positive y values, that means our particle is going to be moving to the right. If we have negative y values, it means our particle is going to be moving to the left. So here, we can't really see it, but we know that our parabola is going to keep going up and getting closer and closer and closer to our y-axis here. So we have positive y values until we get to that time of 1 second. So from 0 to 1 second, since our velocity is positive, our particle is moving to the right. Then, from 1 second to 3 seconds, all of the y values of our velocity function are negative values. So since we have negative values, that means from 1 second to 3 seconds, we're moving to the left. And then after 3 seconds, we keep going up on our parabola. We get into those positive y values again. So after 3 seconds, our particle is moving to the right. And then we also wanted to know at what values of t does a particle change directions? Well, the particle changes directions after it's been at rest at 1 and 3 seconds. We went from moving to the right to moving to the left to moving to the right. So the particle changes directions at t equals 1 and t equals 3.